Hi, my name is Pinosky, and I'm a graduate student in the Center for Robotics and Biosystems at Northwestern University. I will be presenting work done at Northwestern with collaborators Ian Abraham, Alexander Broad, Brenna Argall, and Todd Murphey, titled Hybrid Control for Learning Motor Skills. This work was motivated by the problem of enabling robots to efficiently learn motor skills by combining hard-coded experiences with model-based reasoning. We care about this problem because robots with good models of their environment and their dynamics are capable of incredible feats. However, when robots encounter something in the environment that is unmodeled, our robots tend to fail. Unfortunately, often the thing that has been experienced is difficult to model, such as discontinuous events, and therefore, we often have to hard-code events into the robot. The question is, how do you combine the benefits of model-based reasoning with these necessary hard-coded experiences? Before we dive into the details, this slide provides a summary of some of our results. All of these videos are simulated in the pi-billet half-cheetah environment. For this task, the goal is to get the robot to run as quickly as possible. The video on the left shows an example of the result of model-based learning. As you can see, the half-cheetah initially succeeds in the running task, but is unable to recover once it falls. The video on the right shows an example of model-free learning. In this example, the behavior evolves over time and manages to figure out how to tip back over from the upright position, but it never gains enough experience to really accomplish the running task. The middle video shows that our hybrid learning approach, which systematically combines the two methods, results in improved performance at the running task and learns quite quickly. Before we go into our approach, let's introduce some background information on robot learning. Robot learning can generally be divided into two categories: model-based learning and model-free learning. On the left, model-based learning uses a state transition model to predict subsequent states and choose the reward maximizing action. While on the right, model-free learning uses a learned policy, which encodes state action mapping to choose the global maximizing solution from a reactive lookup table. Where does the state transition model come from? The state transition model is learned from the dynamics model and rewards models. Subsequent actions are then planned using predictions from the learned model. This method tends to be sample efficient, but the model quality governs performance, so when implemented, these methods often have poor performance. Where does the policy come from? The only similarity between the model-based version and the model-free version is that a reward function is used to evaluate performance. But because there is no model of the dynamics, past experience is required to learn the mapping between states and actions. Since this method learns through experience, it is not sample efficient, but it tends to have better performance than model-based methods. This table provides a summary of the information provided on the previous slide. Although model-based learning is more sample efficient, model-free learning has higher performance. The question we want to answer is, can we improve robot learning of motor skills by combining these various modes of learning? One way of approaching this task is to formulate learning as a mode scheduling problem. This will allow us to combine the model-free and model-based methods. We can rely on the policy to guide model-based planning if there is uncertainty. Perhaps an example will help illustrate the approach. For this task, our goal is to reach the goal position while avoiding obstacles in the form of a fire pit, an alligator, and a hurdle. Our model-free policy may have previously experienced the first two obstacles and know to avoid the fire pit and the alligator. But it never experienced the hurdle, so it may not be able to ultimately reach the goal. Meanwhile, our model-based version may know the hurdle exists and be able to avoid it, but it's unaware of the first two obstacles, so it will never ultimately reach the goal. Hybrid learning will allow us to optimally combine the knowledge from both learning methods to successfully avoid all three obstacles and reach the goal. Okay, so we said hybrid learning can be formulated as a mode scheduling problem. What does that mean? Well, in hybrid control theory, the goal of mode scheduling problem is to maximize the reward through the synthesis of two or more control strategies, also called modes. This maximization is achieved by optimizing when to switch which policy is controlled at each instance, subject to the dynamics. So the reward, which is represented by J, is optimized with respect to switching time tau and duration lambda. For our learning problem, we can set the default strategy to be the model-free policy, mu. The objective will then decide when to switch to the model-based policy, represented by A hat. We can convert this problem statement into a simpler problem. Given a suboptimal policy pi, what is the best action the robot can take to maximize the reward at any time during the time horizon, subject to the uncertainty of the policy? With this problem, we can solve for the optimal control A star at any time that improves the reward with respect to the switching time between model-free and model-based controls. This allows A star to be calculated and applied recursively as a receding horizon control problem. Let's break down the equation. The partial derivative term tells us how much the reward changes from switching from a model-free policy to model-based planning. The constraints on the cost also encode the model-based planning information. The log term makes sure the control is close to the model-free policy if it has high confidence. High confidence in the policy implies consistent high reward behavior. If the partial derivative term is 0 for all potential switching times tau, then the model-free policy is optimal. If we assume the policy is a normal distribution, then A star has a closed-form solution during a fixed time horizon. This means that when the model-free policy variance represented by sigma is small, the control relies on the model-free policy. When the variance is large, the control is augmented with model-based planning. So the sigma and mu in this equation come from the model-free policy, and the h comes from the model-based mapping, and rho comes from the reward function. This brings us back to the simulated results that were shown in the beginning of this presentation. Soft actor critic, or SAC, was used to generate the model-based results on the left. A model-based controller was used for the model-free results on the right, and the center shows the results of implementing our hybrid learning method in simulation. These results showed that the hybrid learning method improves optimal policy learning efficiency by 2 to 4 times when compared to these state-of-the-art methods alone. We also applied hybrid learning to real robot experiments. In this experiment, we used a Sawyer robot whose goal was to push a block on a table to a specified marker. The position of the marker and the position of the block are known to the robot. What makes this task difficult is that the robot needs to discover the contact between the arm and the block in order to complete the pushing task. Our hybrid learning approach is able to learn the task within 20 episodes, where each episode took about 10 seconds. Since our method naturally relies on the predictive models when the policy is uncertain, the robot is able to plan through contact to achieve the task, whereas SAC takes significantly longer to discover the pushing dynamics. As a result, we are able to achieve the task with minimal environment interaction. We also extended our method to use expert demonstrations as experience, using experiments with the Franka Panda robot. The goal was for the robot to learn to stack one block on top of another block using demonstrations. A demonstration was provided at each attempt of the task to learn the policy, to update the learned policy. Experience was only used to update predictive models. 10 pre-collected demonstrations were provided before testing. demonstrations may vary around the arm's initial position, causing imitated actions to have state drift. This drift results in a covariant shift problem, leading to poor performance for behavior cloning alone. Our approach was capable of learning the task in as little as 2 demonstrations, where the behavior cloning alone suffers from poor performance. Since our approach synthesizes actions when the policy is uncertain, the robot is able to interpolate between regions where the expert demonstrations were lacking, enabling the robot to achieve the task. In conclusion, we showed that hybrid learning improves robot learning efficiency through optimal combination of learning modes. We showed hybrid learning can be implemented on both simulated and physical robotic systems, and we demonstrated that demonstrations can be an effective form of bootstrap. And finally, dirty laundry. First, optimality of the policy requires the learned model be accurate at the optimal solution. As a result, verification of optimality is only approximate. Second, the gradient-based solution required fine-tuning. Third, exploration is still done through random sampling. Depending on the task's complexity and dimensionality, random sampling may not be sufficient to gain diverse experience for the model-free policy to significantly contribute to the controller. And finally, this method is still an implementation of reinforcement learning at the end of the day, so verifying correctness is hard. Thank you for listening to this presentation on hybrid control for learning motor skills.